additional citations for verification. Please help improve this article by adding citations to reliable sources in this section. Unsourced material may be challenged and removed. Find sources: Transistor News Times, Newspapers Times, Books Times, Scholar Times, Chester, December 2020. Learn how and when to remove this message. Transistors are categorized by 1. Structure: MOSFET, IGFET, BJT, JFET, insulated gate bipolar transistor, IGBT, other types. 2. Semiconductor material, dopants. 1. The metalloids: germanium, first used in 1947, and silicon, first used in 1954, in amorphous, polycrystalline and monocrystalline form. 2. The compounds gallium arsenide, 1966, and silicon carbide, 1997. 3. The alloy silicon germanium, 1989. 4. The allotrope of carbon graphene, research ongoing since 2004, etc. See semiconductor material. 3. Electrical polarity, positive and negative NPN, PNP, BJTs, N-channel, P-channel, FETs. 4. Maximum power rating, low, medium, high. 5. Maximum operating frequency, low, medium, high, radio, RF, microwave frequency. The maximum effective frequency of a transistor in a common emitter or common source circuit is denoted by the term foot, an abbreviation for transition frequency, the frequency at which the transistor yields unity voltage gain. 6. Application: switch, general purpose, audio, high voltage, superbeta, matched pair. 7. Physical packaging: through-hole metal, through-hole plastic, surface mount, ball grid array, power modules, see packaging. 8. Amplification factor HFE, F, transistor beta, or gram, transconductance. 9. Working temperature, extreme temperature transistors and traditional temperature transistors, 55 to 150 degrees Celsius, 67 to 302 degrees Fahrenheit. Extreme temperature transistors include high temperature transistors, above 150 degrees Celsius, 302 degrees Fahrenheit, and low temperature transistors, below 55 degrees C, 67 degree F. The high temperature transistors that operate thermally stable up to 250 degrees Celsius, 482 degrees Fahrenheit, can be developed by a general strategy of blending interpenetrating semicrystalline conjugated polymers and high glass transition temperature insulating polymers. Hence, a particular transistor may be described as silicon, surface mount, BJT, NPN, low power, high frequency switch. Mnemonics, edit. Convenient mnemonic to remember the type of transistor, represented by an electrical symbol, involves the direction of the arrow. For the BJT, on an NPN transistor symbol, the arrow will not point in. On a PNP transistor symbol, the arrow points in proudly. However, this does not apply to MOSFET-based transistor symbols as the arrow is typically reversed, i.e. the arrow for the NPN points inside. Field effect transistor, FET, edit. Main article, field effect transistor. See also, JFET. The field effect transistor, sometimes called a unipolar transistor, uses either electrons, in N-channel FET, or holes, in P-channel FET, for conduction. The four terminals of the FET are named source, gate, drain, and body, substrate. On most FETs, the body is connected to the source inside the package, and this will be assumed for the following description. In a FET, the drain to source current flows via a conducting channel that connects the source region to the drain region. The conductivity is varied by the electric field that is produced when a voltage is applied between the gate and source terminals. Hence the current flowing between the drain and source is controlled by the voltage applied between the gate and source. As the gate source voltage, VGS, is increased, the drain source current, IDs, increases exponentially for VGS below threshold, and then at a roughly quadratic rate, ID's proportionality, VGS VT, where VT is the threshold voltage at which drain current begins, in the space charge limited region above threshold. A quadratic behavior is not observed in modern devices, for example, at the 65 nm technology node. For low noise at narrow bandwidth, the higher input resistance of the FET is advantageous. FETs are divided into two families, junction FET, JFET, and insulated gate FET, IGFET. The IGFET is more commonly known as a metal oxide semiconductor FET, MOSFET, reflecting its original construction from layers of metal, the gate, oxide, the insulation, and semiconductor. Unlike IGFETs, the JFET gate forms a PN diode with the channel which lies between the source and drains. Functionally, this makes the N-channel JFET the solid-state equivalent of the vacuum tube triode which, similarly, forms a diode between its grid and cathode. Also, both devices operate in the depletion mode, they both have a high input impedance, and they both conduct current under the control of an input voltage. Metal semiconductor FETs, MESFETs, are JFETs in which the reverse biased PN junction is replaced by a metal semiconductor junction. These, and the HEMTs, high electron mobility transistors, or HFETs, in which a two-dimensional electron gas with very high carrier mobility is used for charge transport, are especially suitable for use at very high frequencies, several gigahertz. FETs are further divided into depletion mode and enhancement mode types, depending on whether the channel is turned on or off with zero gate to source voltage. For enhancement mode, the channel is off at zero bias, and a gate potential can enhance the conduction. For the depletion mode, the channel is on at zero bias, and a gate potential, of the opposite polarity, can deplete the channel, reducing conduction. For either mode, a more positive gate voltage corresponds to a higher current for N-channel devices and a lower current for P-channel devices. Nearly all JFETs are depletion mode because the diode junctions would forward bias and conduct if they were enhancement mode devices, while most IGFETs are enhancement mode types. Metal oxide semiconductor FET, MOSFET, edit. Main article, MOSFET. The metal oxide semiconductor field effect transistor, MOSFET, MOSFET, or MOSFET, also known as the metal oxide silicon transistor, MOS transistor, or MOS, is a type of field effect transistor that is fabricated by the controlled oxidation of a semiconductor, typically silicon. It has an insulated gate, whose voltage determines the conductivity of the device. This ability to change conductivity with the amount of applied voltage can be used for amplifying or switching electronic signals. The MOSFET is by far the most common transistor, and the basic building block of most modern electronics. The MOSFET accounts for 99.9% of all transistors in the world. Bipolar junction transistor, BJT, edit. Main article, Bipolar junction transistor. Bipolar transistors are so named because they conduct by using both majority and minority carriers. The bipolar junction transistor, the first type of transistor to be mass-produced, is a combination of two junction diodes and is formed of either a thin layer of P-type semiconductor sandwiched between two N-type semiconductors, an NPN transistor, or a thin layer of N-type semiconductor sandwiched between two P-type semiconductors, a PNP transistor. This construction produces two p-n junctions, a base emitter junction and a base collector junction, separated by a thin region of semiconductor known as the base region. Two junction diodes wired together without sharing an intervening semiconducting region will not make a transistor. BJTs have three terminals, corresponding to the three layers of semiconductor, an emitter, a base, and a collector. They are useful in amplifiers because the currents at the emitter and collector are controllable by a relatively small base current. In an NPN transistor operating in the active region, the emitter base junction is forward biased, electrons and holes recombine at the junction, and the base collector junction is reverse biased, electrons and holes are formed at, and move away from, the junction, and electrons are injected into the base region. Because the base is narrow, most of these electrons will diffuse into the reverse biased base collector junction and be swept into the collector. Perhaps 1/100th of the electrons will recombine in the base, which is the dominant mechanism in the base current. As well, as the base is lightly doped, in comparison to the emitter and collector regions, recombination rates are low, permitting more carriers to diffuse across the base region. By controlling the number of electrons that can leave the base, the number of electrons entering the collector can be controlled. Collector current is approximately beta, common emitter current gain, times the base current. It is typically greater than 100 for small signal transistors but can be smaller in transistors designed for high power applications. Unlike the field effect transistor, see below, the BJT is a low input impedance device. Also, as the base emitter voltage, VBE, is increased, the base emitter current and hence the collector emitter current, ICE, increase exponentially according to the Shockley diode model and the Abas-Morel model. Because of this exponential relationship, the BJT has a higher transconductance than the FET. Bipolar transistors can be made to conduct by exposure to light because the absorption of photons in the base region generates a photocurrent that acts as a base current. The collector current is approximately beta times the photocurrent. Devices designed for this purpose have a transparent window in the package and are called phototransistors. Usage of MOSFETs and BJTs, edit. The MOSFET is by far the most widely used transistor for both digital circuits as well as analog circuits, accounting for 99.9% of all transistors in the world. The bipolar junction transistor, BJT, was previously the most commonly used transistor during the 1950s to 1960s. Even after MOSFETs became widely available in the 1970s, the BJT remained the transistor of choice for many analog circuits such as amplifiers because of their greater linearity, up until MOSFET devices, such as power MOSFETs, and MOS and RFMOS, replaced them for most power electronic applications in the 1980s. In integrated circuits, the desirable properties of MOSFETs allowed them to capture nearly all market share for digital circuits in the 1970s. Discrete MOSFETs, typically power MOSFETs, can be applied in transistor applications, including analog circuits, voltage regulators, amplifiers, power transmitters, and motor drivers. Other transistor types, edit. For early bipolar transistors, see bipolar junction transistor. Bipolar transistors. 1 field effect transistor, FET. 1 metal oxide semiconductor field effect transistor, MOSFET, where the gate is insulated by a shallow layer of insulator. 1 p-type MOS, PMOS. 2 n-type MOS, MOS. 3 complementary MOS, CMOS. 1 RFMOS, for radio frequency amplification, reception. 4 multigate field effect transistor, MUGFET. 1 fin field effect transistor, FIN-FET, Source /drain region shapes fins on the silicon surface. 2. Garfet, similar to fin FET but nanowires are used instead of fins. The nanowires are stacked vertically and are surrounded on 4 sides by the gate. 3. Infet, a variant of Garfet that uses horizontal nanosheets instead of nanowires, made by Samsung. Also known as ribbon FET, made by Intel, and as horizontal nanosheet transistor. 5. Thin film transistor, TFT, used in LCD and OLED displays. Types include amorphous silicon, LTPS, LTPO and IGZO transistors. 6. Floating gate MOSFET, FMOS, for non-volatile storage. 7. Power MOSFET, for power electronics. 1. Lateral diffused MOS, LDMOS. 2. Carbon nanotube field effect transistor, CFET, where the channel material is replaced by a carbon nanotube. 3. Ferroelectric field effect transistor, FEFET, uses ferroelectric materials. 4. Junction gate field effect transistor, JFET, where the gate is insulated by a reverse biased PN junction. 5. Metal semiconductor field effect transistor, MESFET, similar to JFET with a Schottky junction instead of a PN junction. 1. High electron mobility transistor, HEMT-GaN, gallium nitride, SiC, silicon carbide, Ga203, gallium oxide, GaAs, gallium arsenide, transistors, MOSFETs, etc. 6. Negative capacitance FET, NCFET. 7. Inverted T field effect transistor, ITFET. 8. Fast reverse epitaxial diode field effect transistor, FREDFET. 9. Organic field effect transistor, UFET, in which the semiconductor is an organic compound. 10. Ballistic transistor, disambiguation. 11. FETs used to sense the environment. 1. Ion-sensitive field effect transistor, ISFET, to measure ion concentrations in solution. 2. Electrolyte oxide semiconductor field effect transistor, EOSFET, Neurochip. 3. Deoxyribonucleic acid field effect transistor, GNAFE. 4. Field effect transistor-based biosensor, BioFET. 2. Bipolar junction transistor, BJT. 1. Heterojunction bipolar transistor, up to several hundred GHz, common in modern ultrafast and RF circuits. 2. Schottky transistor. 3. Avalanche transistor. 4. Darlington transistors are 2 BJTs connected together to provide a high current gain equal to the product of the current gains of the 2 transistors. 5. Insulated gate bipolar transistors, IGBTs, use a medium power IGFET, similarly connected to a power BJT, to give a high input impedance. Power diodes are often connected between certain terminals depending on specific use. IGBTs are particularly suitable for heavy-duty industrial applications. The ASEA Brown Boveri, ABB, 5SNA 2400E170100, intended for 3-phase power supplies, houses 3 NPN IGBTs in a case measuring 38 by 140 by 190 mm and weighing 1.5 kilograms. Each IGBT is rated at 1700 volts and can handle 2400 amperes. 6. Phototransistor. 7. Emitter-switched bipolar transistor, ESBT, is a monolithic configuration of a high-voltage bipolar transistor and a low-voltage power MOSFET in cascode topology. It was introduced by ST Microelectronics in the 2000s, and abandoned a few years later around 2012. 8. Multiple emitter transistor, used in transistor logic and integrated current mirrors. 9. Multiple base transistor, used to amplify very low-level signals in noisy environments such as the pickup of a record player or radio front ends. Effectively, it is a very large number of transistors in parallel where, at the output, the signal is added constructively, but random noise is added only stochastically. 3-tunnel field effect transistor, where it switches by modulating quantum tunneling through a barrier. 4 diffusion transistor, formed by diffusing dopants into semiconductor substrate, can be both BJT and FET. 5 unijunction transistor, which can be used as a simple pulse generator. It comprises the main body of either P-type or N-type semiconductor with ohmic contacts at each end, terminals base 1 and base 2. A junction with the opposite semiconductor type is formed at a point along the length of the body for the third terminal, emitter. 6 single electron transistors, set, consist of a gate island between 2 tunneling junctions. The tunneling current is controlled by a voltage applied to the gate through a capacitor. 7 nanofluidic transistor, controls the movement of ions through submicroscopic, water-filled channels. 8 multigate devices. 1 tetrode transistor. 2 pentode transistor. 3 triggered transistor, prototype by Intel. 4 dual gate field effect transistors have a single channel with 2 gates in cascade, a configuration optimized for high-frequency amplifiers, mixers, and oscillators. 9 junctionless nanowire transistor, JNT, uses a simple nanowire of silicon surrounded by an electrically isolated wedding ring that acts to gate the flow of electrons through the wire. 10. Nanoscale vacuum channel transistor, when in 2012, NASA and the National Nanofab Center in South Korea were reported to have built a prototype vacuum channel transistor in only 150 nanometers in size, can be manufactured cheaply using standard silicon semiconductor processing, can operate at high speeds even in hostile environments, and could consume just as much power as a standard transistor. 11 organic electrochemical transistor. 12 solaristor, from solar cell transistor, a 2-terminal gateless self-powered phototransistor. 13 germanium tin transistor. 14 wood transistor. 15 paper transistor. 16 carbon-doped silicon germanium, SiGEC, transistor. 17 diamond transistor. 18 aluminum nitride transistor. 19 superlattice castellated field effect transistors. Device identification, edit. 3 major identification standards are used for designating transistor devices. In each, the alphanumeric prefix provides clues to the type of the device. Joint Electron Device Engineering Council, JEDEC, edit. The JEDEC part numbering scheme evolved in the 1960s in the United States. The JEDEC EIA 370 transistor device numbers usually start with 2N, indicating a 3-terminal device. Dual-gate field effect transistors are 4-terminal devices, and begin with 3N. The prefix is followed by a 2, 3 or 4-digit number with no significance as to device properties, although early devices with low numbers tend to be germanium devices. For example, 2N3055 is a silicon NPN power transistor, 2N1301 is a PNP germanium switching transistor. A letter suffix, such as a, is sometimes used to indicate a newer variant, but rarely gain groupings. JEDEC prefix table. Prefix type and usage. 1N 2-terminal device, such as diodes. 2N 3-terminal device, such as transistors or single-gate field effect transistors. 3N 4-terminal device, such as dual-gate field effect transistors. Japanese Industrial Standard, JIS, edit. In Japan, the JIS semiconductor designation, JISC 7012, labels transistor devices starting with 2S, for example, 2SD965, but sometimes the 2S prefix is not marked on the package. A 2SD965 might only be marked D965 and a 2SC1815 might be listed by a supplier as simply C1815. This series sometimes has suffixes, such as R, O, BL, standing for red, orange, blue, etc., to denote variants, such as titer HFE, gain, groupings. JIS transistor prefix table. Prefix type and usage. 2SA high frequency PNP BJT. 2SB audio frequency PNP BJT. 2SC high frequency NPN BJT. 2SD audio frequency NPN BJT. 2SJP channel FET, both JFET and MOSFET. 2SKN channel FET, both JFET and MOSFET. European Electronic Component Manufacturers Association, EECA, edit. The European Electronic Component Manufacturers Association, EECA, uses a numbering scheme that was inherited from Pro Electron when it merged with EECA in 1983. This scheme begins with two letters. The first gives the semiconductor type, A for germanium, B for silicon, and C for materials like GaAs. The second letter denotes the intended use, A for diode, C for general-purpose transistor, etc. A three-digit sequence number, or one letter and two digits, for industrial types, follows. With early devices this indicated the case type. Suffixes may be used, with a letter, for example C often means high HFE, such as in BC549C, or other codes may follow to show gain, for example BC327-25, or voltage rating, for example BUK854-800. The more common prefixes are EECA transistor prefix table. Prefix type and usage example equivalent reference. AC germanium, small signal AF transistor AC126NTE1020. AD germanium, AF power transistor AD133NTE179. AF germanium, small signal RF transistor AF117NTE160. AL germanium, RF power transistor ALZ10NTE100. As germanium, switching transistor ASY28NTE101. Or germanium, power switching transistor 103 Australian dollars NTE127. BC silicon, small signal transistor, general purpose, BC5482N3904 datasheet. BD silicon, power transistor BD139NTE375 datasheet. BF silicon, RF, high frequency, BJT or FET BF245NTE133 datasheet. BS silicon, switching transistor, BJT or MOSFET, BS172N7000 datasheet. BL silicon, high frequency, high power, for transmitters, BLW60NTE325 datasheet. BU silicon, high voltage, for CRT horizontal deflection circuits, BU2520 NTE2354 datasheet. CF gallium arsenide, small signal microwave transistor, MESFET, CF739, datasheet. CL gallium arsenide, microwave power transistor, FET, CLY10, datasheet. Proprietary, edit. Manufacturers of devices may have their proprietary numbering system, for example CK722. Since devices are second-sourced, a manufacturer's prefix, like MPF in MPF-102, which originally would denote a Motorola FET, now is an unreliable indicator of who made the device. Some proprietary naming schemes adopt parts of other naming schemes. For example, a PN2222 is a, possibly Fairchild semiconductor, 2N2222 in a plastic case, but a PN108 is a plastic version of a BC108, not a 2N108, while the PN100 is unrelated to other XX100 devices. Military part numbers sometimes are assigned their codes, such as the British military.